morning, Earth Space. Today we are going to start learning about plate tectonics. So, the big story we're going to be telling is how the Earth used to be shaped in a pretty different way than it was before. Now, of course, the Earth was still round, but the continents were part of a supercontinent called Pangaea. Continental drift happened that separated Pangaea. Continental drift is when, over time, the continents are in constant motion on the surface of the Earth and they separated. We have some evidence that supports Pangaea, but of course we've never seen it ourselves. The continents seem to fit together like puzzle pieces if we could push them around. And if we put them all together, they would form Pangaea like we think it looked like in the past, before continental drift broke it apart. There are other clues for Pangaea other than that kind of puzzle look. There are clues from climate patterns like weather, the fossils we found on different continents, and the types of rocks we found on different continents. And all of those together led to continental drift theory. Continental drift theory helps us create maps of ancient land and water patterns based on investigations of rocks and fossils, and those rocks and fossils make it clear how Earth's tectonic plates have moved huge distances. They've collided in the past, and ones that were together have spread apart. So we've been saying tectonic plate a lot, and let's define it. A tectonic plate is a really big piece of the lithosphere. Remember, that's the cold and hard outer rock layer right under the Earth's crust. So, for instance, you might have an ocean, a thin layer of crust, and then the lithosphere. I think the lithosphere is your very, very top part of the mantle. Underneath that, we have the asthenosphere. That's right underneath the lithosphere. It's hot and it acts like it's plastic, so it's movable and it's meltable. So again, our image of that is like a crust, a solid crust, the lithosphere on top of some jello. The jello can wiggle, the jello can melt, and the jello moving is going to move the top crust. These two spheres, the lithosphere and the asthenosphere, work together, and the heat of the asthenosphere causes it to melt, and that melting allows the plates of the lithosphere to move, and those moving plates are plate tectonics. In this picture, you can see these little rotating arrows of the asthenosphere's heat making the asthenosphere move, and that motion underneath is bumping around those plates in the lithosphere. The theory of plate tectonics defined is that Earth's surface is made of rigid slabs of rock, or plates, that are the Earth's crust on top of the lithosphere. And they move slowly with respect to one another. They might collide, they might spread apart, and they might slide past each other. The biggest one is the Pacific Plate, the smallest one is Juan de Fuca Plate, and the boundaries are throughout oceans, and we have these mid-ocean ridges and really cool pieces of evidence that show us what is happening underneath the ground. We are going to learn the three flavors of plate boundaries. It's when two plates meet and move together, or when they move apart, or when they move past each other. So take a look on the left at a divergent plate boundary. That's when two plates separate from each other. So the tectonic plates are pulling apart, and hot, like lava type stuff from the asthenosphere is coming up between the gap. So we're literally getting new lithosphere. We're getting new crust as these plates pull apart and new rock is created by that flow of lava. This happens a lot underneath the ocean. Second, we have a transform plate boundary. Those two plates are sliding past each other. It's not going to change the amount of crust or the amount of lithosphere. They're just grinding, sliding past each other. And third, we have convergent plate boundaries, which is when the two plates collide. We can have a few different things happen here, but one of them is we can actually lose surface area of Earth because one plate slides underneath the other and kind of sinks deeper into the mantle. Here's our divergent boundary. The two plates have separated. This happens on the seafloor, and it's called a mid-ocean ridge. So on the left side, you see this happening underneath the ocean, and in the middle, that red kind of lava bubbling up is a divergent boundary. The new lava is going to solidify as the plates pull apart, so there's new rock in the middle. So the rock furthest from the boundary is the oldest, and the rock closest to the boundary is the newest, because it actually just came out of the asthenosphere through that gap that we've made as the plates pull apart. Next, we have a divergent plate boundary that is in between two continents. So there's no water, there's no ocean. This is just right in the open air. We can also have this kind of divergent boundary, and the same idea is going to happen. You're going to have parts of the asthenosphere come up through that gap, and the newest rock is in the center. The oldest rock is towards the edge. Seafloor spreading is what happens when new ocean crust forms along that mid-ocean ridge. The old crust is moving away continually as the plates drift apart. This is most of how our continents move and how they spread all across the Earth, like in continental drift after Pangaea was formed. It happens at mid-ocean ridges, and it gives us some interesting topography on the seafloor. You can see some really cool little tiny ridges all across the ocean, and that's the evidence of seafloor spreading, of a divergent plate boundary under the ocean. And this helps us explain how the continents moved over time. A transform boundary is different, and it's how you form a fault, if you've ever heard of like San Andreas Fault. And along transform boundaries, earthquakes are common as the plates grind past each other. The most famous one, again, is the San Andreas Fault along the coast of California. Here you see that there's no asthenosphere coming up, there's no crust sinking, the plates are just sliding past each other. You can see evidence of this with your naked eye, so this is an image of a transform plate boundary, and there might be earthquakes that come from that zone as the plates move. Okay, last one, the convergent plate boundary when worlds collide. This can happen when an ocean plate collides with a continent plate. And subduction will happen as they collide because the denser ocean plate is going to sink below the more buoyant land plate. That's going to create a trench as one thing sinks, and it's also going to form a volcano as the other's kind of pushed up. So we're talking about this very top image. On the left, you have an oceanic plate, and it's going through subduction because it collided with a more buoyant continental plate and is sinking. So at this boundary, we have a deep sea trench forming. You can also have a volcano form at the continental plate in a convergent plate boundary. The next image is a convergent boundary that's just completely and entirely under the ocean. Again, whichever plate is the densest is going to be the plate that goes through subduction. And at this convergent boundary, we have a deep sea trench. We're kind of getting a pit as they collide. This last one is a convergent boundary that is just two continental plates coming together. It's the same idea. One plate is sinking under another one, and this is going to help us form mountains, not volcanoes. The volcanoes are happening between oceanic and continental, to be clear. So these tectonic processes are going to generate new ocean seafloor ridges when they pull apart. So a divergent boundary creates more seafloor. But a convergent boundary is going to destroy old seafloor as it sinks into the trench. So we create new crust as plates pull apart, and we destroy old crust as plates come together through convergent boundaries and subduction. When continent and continent plates collide, sometimes there's no subduction at all. They collide and they both push each other up and they form mountains. And that's how we can explain huge mountain ranges like the Himalayas. That's why mountain ranges occur in lines, because they're forming along the edges of two huge tectonic plates. That's all I got about the plates for you today. I hope it was a good time. Ask me any questions. See you later.